I think I got it. Probably what had happened was X was caps and I did it small. So shift run. Okay, good. So it is accepted now. So predict output. So we have got the Y predict run already. Now in this equation, Y pred is the predicted value column. Regression model is the regression model we generated by training the data, and X test is the test data array. So below we define another table data frame df that has actual test values listed in a column named actual and the respective predicted values in a separate column predicted. So let's do that part now. Df, let's define a new one. Df equal to pd dot data frame, d caps data frame round bracket. Now we define a dictionary here. So open braces, open quotes, actual. This is the column name is to y underscore test, comma, single quotes, predicted. This is another column. These will appear as column names, and under predicted column we will have all the y underscore pred values, right? Now let's check first 25 rows df1. df1 will define another. Now we know already this instruction df dot head 25. So what we are doing here? So we are just comparing actual values and predicted values. In a data frame we are going to create called df, and out of that 25 rows will be another copy called df1. So let's do that part. Shift enter. So we have created this part. Now evaluation of the performance. We have already run the model. We have generated the output values. We are going to evaluate the performance now. Essentially, under validation, we want to check how accurately the algorithm has predicted the mileage. For that is, compare predicted values with the actual values from the test data. We shall do three types of validations. First one is the visual check. Second one is the percentage predictions, where the predicted versus actual error is say within plus or minus 10% variance. See, normally this will be defined by some user, some client, that we want so much accuracy within this limit, and we should have so many percentage of samples at least, which will conform to this accuracy. So we are setting up a 10% variance, and we'll measure this again. This is the benchmark we'll set, and we'll compare against that. Then third one is the root mean square error percentage, which is the statistical benchmark. This is actually universally accepted one. So now we will do a visual comparison. Below bar chart represents a comparison between individual and predicted value and actual value to get an idea. This is a standard plot syntax. So let's copy this instead of typing it one by one. So I do copy, and the first part will simply paste here. Okay. So let's go run through that instruction. df1.plot. Okay. So this is matplotlib, which is going to plot it for us. Then kind equal to bar. We want it as a form of bars. Okay. Figure size 10,6. This is the size. You can change this option to whatever numbers you want. Now, which is major axis, which is minor axis. These are all finer points we want to set there. The different colors. What colors of bars we want? Green, black, blah, blah, whatever. So this is all standard process. You would be knowing this. So I'm just not going to go into the details. And then plot plt.show. Shift enter. Okay. So here is the bar plot. This is actually giving us just a quick check, a visual representation as how's the predicted and actual values, how close or how far these are. Okay, actual and predicted, we are just comparing. So this was the first type of check we did. Now these two are important. Percentage prediction within tolerance. Now this I found in the industry, this is most relevant. We shall record the entire test output generated and calculate how many predictions are within plus or minus say 10% variance, as we discussed. See, this will generate an Excel sheet which will be saved on my C drive. Similarly, you can give a path where you will want to save it on your drive. Okay, and then you can open and take a look at how the different columns are appearing. I'm going to give a snapshot below, which is the performance we are expecting to get out of this data. So initial performance. So let us do this part first. Prediction with tolerance. Okay. Now within tolerance, df0, it will define another data frame here. df0 equal to df. This was our above data frame, earlier one. df.head 79. Why 79? Because we have 79 test samples. df0 dot 2 underscore 2 CSV. This is a standard method. You must be knowing this. df0 dot 2 CSV, and then I'm going to give the entire path. So I will just copy this path. You can whatever path that suits you. Control C. I'm going to put this path here. C:/users was cars out base. So this is the base run. So you can name it as cars out base, and this will keep record. We'll compare as we improve the performance. Now shift enter. So this instruction is run. It has generated an output here. So instead, I won't spend time in looking at that. I have given a quick summary here to save the time. So this is the kind of look we are getting at the Excel sheet. Actual, predicted, error percentage, percentage prediction within 10%. So this is not a very great accuracy we are getting here, but we are going to improve this by a couple of changes that we will discuss it next. Okay. So this is now saying 57% of the predictions are right and 43% are off. They are outside 10% variance. Now the third type of thing that we are going to do is, again, this is a standard syntax, so let's not spend a lot of time on typing this. So there are three things: mean absolute error, mean squared error, and root mean squared error. Our main interest is root mean squared error. So these steps are just to know step by step how things are there, and so that we can look back and check. It's not, so this is something that you can try it out by yourself and get a feel. Right now I'm going to get the numbers finally. Shift enter. So mean absolute error is matrix.mean absolute error. So this is matrix is one of the libraries. I will just, we must take a note of this. Matrix is the library we imported from Pandas Python standard libraries. Matrix.mean absolute error. So this is their own field, and we are going to compare y-test, y-pred. So likewise, we have matrix mean squared error and matrix.mean squared root mean squared error. np.sqrt will get the square root of this. Now we'll run this instruction. Shift enter. So we will not go into all the details. We just look at the final value, that is 2.978. That's almost like 3. So 3% is a root mean square error we are getting. This was our like baseline performance. We just did nothing special. We just ran the train data set, split into train and test. We ran the model, we generated the output, and these are the results. Okay. So now we are going to do first level of improvement in the performance. Now let's see how we will do this. First, now, okay, one more thing. We have gone instruction by instruction. So the same instruction will be repeated again and again, couple of times. So we will not type each and every instruction one by one because we already seen it up there. So I'm going to type, copy a bunch of instructions and run it straight away. So we quickly generate an output. So improvise performance. First approach, select only 4-cylinder data. You remember that up there, we created a library called 4sil. Let's check we have done that part or not. So let me try one thing. I do not remember if we ran that instruction or not. df underscore 4sil dot shape. Shift enter. Okay, so we have it here. So as we remember, we had split the data, that is 394 rows, into the maximum number of 4-cylinder car models. Okay, so these are about 50%, 201. So we have picked up a section of that data of 201 rows and 9 columns. So we will straight away plot a scatter matrix here that we have seen to save our time. This will kind of show us the behavior, but we kind of know how they are related. So I will just, remaining is going to be repetition of what we did. All we are doing, what special we are doing is, we are, instead of having a mix of 4 cylinders, 6 cylinders, 8 cylinders, we are segregating 4 cylinders together. They are machine learning. Normally the principle that we need to remember is, the more homogeneous data we have, the better results we get. So by keeping 4 cylinders separate, we are expecting to get a better result. So let's see how this happens. So I copy this here. So we generate a scatter matrix for DF4 cell, shift enter. Okay, so it is generating the matrix for us. So we can take a look. Okay, if we scroll down here, now this is showing us the behavior. Now here this is showing, what we showing is, we are having only half of the data here, but more uniform data. And we are seeing that the displacement, these are all displacement, these are bivariate plots. Mileage is plotted with displacement, then number of the year, the weight, the displacement, and all these fields. And we're going to repeat the earlier process once again. So set up the data. So I will just execute a bunch of instructions here. Set up the data, predictors, and target variable. So this is a repetition of what we discussed earlier. So DF4 cell is our, then we are pd.get dummies. Again we are going as before. Origin field, we are going to get the categorical into numeric values. Then we are defining X, we are defining Y, we are splitting train test, and we are setting up the data for the model. And finally it will check the X test dot shape, that will give the shape of this. Shift enter. So out of this, what comes out is, we have 41 rows only and 8 columns as the test data, and remaining out of 201, that's roughly 160 are trained data. So define and train the model. So let's go to that step now. So again we will execute a bunch of instructions here. We will not waste time in typing this once again, because you can try it out yourself and see how it improves the model performance. Control V. So shift enter. So here are the coefficients we have generated, the predictors and the coefficients. Next one is predict the output. So these are again repetition of what we did earlier. Control C. Now quickly come to the evaluation.